Alright, so this video, the first video in our Chapter 5 series, we're going to be talking about the natural logarithm. If you have forgotten about logarithms and what they have meant to us in the past, then maybe you should consider going back and watching a video that'll refresh your memory on that. Now, in this section, the natural logarithm has a different definition, and one of the reasons why the natural logarithm is even coming up is because we want to be able to expand our ability to take derivatives and antiderivatives. So let me show you what I'm talking about. In general, we can take the derivative, or the antiderivative of something like this, x to the n dx. And how do we do that? We always add 1 to the power, and then what do we do? Well, if we add 1 to the power, and then we try to go backwards, and we say, how do I take the derivative of this? I'll bring this down, I'll multiply by n plus 1, and then I'll subtract 1 from the power. Right? That's how we get that. That's the reasoning that led us to add 1 to the power, because we always subtract 1 from this power. But if I multiply by n plus 1, I'll have n plus 1 times x to the n. This would be n plus 1 times x to the n. But it's not n plus 1, it's 1. So how do we counteract that? Well, that's where we throw that fraction down here in front. Okay, so for example, if we had the antiderivative of x to the third, then we would say, well, we'd add 1 to the power, so that'd be x to the fourth, but when we go to take the derivative, it would be 4x to the third, so we put down a 1/4, so that 4 times 1/4 is 1. Subtract 1, we get x to the third, 1x to the third. Okay, so, and then plus c. Now let's try this. This applies to every power, actually almost every power. That's what we're going to talk about today. Even if I had something like the antiderivative of the square root of x, this can be written as a power of x. It can be written as the antiderivative of x to the 1/2 power, and then we apply this reasoning here. We take x and we raise it to a power of 1 plus a half, which would be 3/2. And then we realize when we take the derivative, we're going to bring down and multiply by 3/2, but we want to get 1, not 3/2. So we put 2/3, the reciprocal of 3/2, so that we get a 1, like we want. Okay. This keeps on working. It works for the antiderivative of 1 over, say, x to the third. As long as we can write it as a power of x, we can apply that rule. So this would be the antiderivative of x to the negative 3. So now we have x to a power. We can add 1 to that power. X to the negative 2. But then if we multiply by negative 2, then we'll get negative 2x to the negative 3. So we put a negative 1/2 right there. So that when we multiply by negative 2, we get a 1. And I've not been a good mathematician here. I need to put plus c. Okay, so here's where we become interested in the natural logarithm. Let's try and take the antiderivative of 1 over just x. 1 over x. If we use our reasoning from here, we'll write this as x to the negative 1. Okay, everything seems fine. And we'll add 1 to this power. Now let's see what happens. All sorts of confusing things happen. We'll get x to the, add 1 to negative 1, you get 0. Okay, and then when we start thinking about going backwards and taking the derivative of this, we're going to bring down the power of 0 and multiply it by x, and we're going to get a derivative of 0. But it's not, the derivative is not supposed to be 0, it's supposed to be 1 over x. Let's look at it a different way. Clearly this can't be the case. X to the 0. Anything to the 0, 1 to the 0, 5 to the 0, 6 to the 0, anything but 0 to the 0, any number but 0 raised to the 0 is equal to 1. And so the fact that the derivative of this winds up being 0 isn't surprising, because the derivative of x to the 0, it would be the derivative of 1, and the derivative of any constant is 0. But we need a function whose derivative is x to the negative 1, or 1 over x. So that's where the natural logarithm comes in. So it turns out that the natural log is equal to the antiderivative from 1 to x. Now this is not the antiderivative, but the definite integral from 1 to x. So specifically, it always starts at 1 and then goes to a number x of some function 1 over t dt. So there's some function 1 over, we could say x dx, but we just want to use x here for some reason. Because really what happens when we take the antiderivative, then x gets plugged in by the fundamental theorem of calculus and so on. But anyway, what essentially we see here is that the antiderivative, in a way, of 1 over t dt is the natural log of x, is this function natural log of x. So this rule, this power rule for integration, works for all powers except for -1. And now this is the rule for that exception of a power of -1. The natural log of x is that link. Okay, so functionally for us, this fact is really just going to enable us to take derivatives of logarithmic functions. Okay, and that might seem like a weird statement that I just made. You might think I have said the wrong thing. We're going to take derivatives, not antiderivatives. I know that all this discussion had to do with antiderivatives, but it all leads down, at least in this section, to taking derivatives of natural log functions. But I'm going to take a little time and explain some stuff about the natural log function. Like I said, if you're rusty on log functions, you should go back and refresh your memory. If you don't want to listen to my explanation of this whole thing, let me just scroll down, give myself some space. If you don't want to do that, here I'm going to draw a little caution triangle. Okay, and if you just don't feel like listening to this whole explanation about the natural log function, just fast forward until you see this thing disappear, and in the end, you'll be able to crunch the numbers and use the stuff we're supposed to learn in this section. Okay, so I'm going to talk about this function, and then when this goes away, you can stop fast forwarding and just catch right up. So this function here is the antiderivative of this function, or if we go the other way, the natural log has like this as its derivative, right? We've talked about that before. So we could look at, to understand what the natural log function is in terms of this definition. Well, first of all, let's start to look at a graph of it. Okay. And by the way, this is for values of x that are bigger than 0. That this works. So from 1 to 3, 1 to 5, even 1 to a half, 1 to 7, or 1 to 1/7 or something like that, this function is defined, but not for values that are less than 0. So anyway, so if we were to look at the antiderivative from 1 to 1 of 1 over t dt, well, we can think of this as like the area under the curve of this function. Whatever this function even looks like, it doesn't matter. The area from 1 to 1 would be nothing. So this would be 0. So when x is 1, then the natural log of 1, when x is 1, the natural log of 1 would be the definite integral from 1 to 1, which would be 0. So at x is 1, right? If f of x equals the natural log of x, then f of 1 is 0. Okay, so we know that this thing goes through the point 1, 0. Okay, and then how do we view the rest of this function? Well, if the natural log and 1 over t have this relationship, then we could look at the function 1 over t as this differential equation, or this differential equation, where the derivative of some function is equal to 1 over t. And so if the derivative of some function equals 1 over t, then the slope of that function, this function, is 1 over t, or really 1 over x. So what value does the slope have at, say, 2? Um, the slope has a value of 1 over 2 at x equals 2. That's really simple. It's just up 1 and over 2, so the slope is something like this. So we could draw slopes of 1/2, approximately. I'm just drawing a bunch of hash marks. This is called the beginnings of a slope field. Okay, so wherever the graph goes, when it goes through this x value, it should have a slope of 1/2. At 1, it has a slope of 1 over 1, so it has a slope of 1. And at, say, 1/2, this function has a slope of 1 over 1/2, which would be 2. So, and at 1 over 3, this function has a slope of 1 over 1 over 3, which would be 3. So it would be really steep. And at 1 over a million, this function, this natural log function, would have a slope of 1 over 1 over a million, or a slope of a million. So the closer it gets to 0, the smaller that fraction gets, the steeper the slope gets. Okay, and the further out we go here, the shallower the slope gets. If I go out here to 7, then the slope will be 1 over 7. So it'll be 1/7. So that'll be not very steep at all. The further out we go, the closer the slope will just get to be flat. Okay, and if we were to fill these in, we would see a gradual progression from a slope of 1 to 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and so on. So if we were to draw a function through all those values, or through those slopes, we would see it do something like this, right? And getting less and less steep, like that. And then getting more and more steep, as we said, like once it gets close to 0, it gets very, very steep. Slopes of a million, slopes of a billion, and so on. Okay, so we see that's the function. We see that this function has a value that's negative for values that are less than 1, and it's positive for values that are more than 1, which makes sense because it is the definite integral from 1 to x of 1 over t dt. So if we look at that function 1 over t dt, okay, it's going to be something like this. 1 over x. It's going to have a appearance like this. And 1 over x does have another part to it. It's a hyperbola, but we will only look at values that are bigger than 0. So if we, I feel like we need to make this bigger. So let's make it a little bigger. Okay, so here's 1 over x. Alright, so for 1, if we look at the area from 1 to the right of 1, which is what we're used to doing, 1 to 3, 1 to 5, 1 to 7, 1 to whatever, then this would be a positive area if we look at the positive definite integral. But if we go to the left of 1, now we go from 1 to, let's say, a half. Okay, if we go backwards, you may remember in our sections about definite integrals, if we go this way, we have a lower limit that's bigger than the upper limit, and essentially what that does is gives us negative, quote, areas, or negative definite integrals. So we see that here with the natural log. It is the area, quote, area under the curve here, and so that essentially bears out in this function here. We get positive areas, right? The value of it is positive. Not the area under this curve, but the value of the function at this point. Say this is 3, so from 1 to 3. The area under this curve from 1 to 3 is whatever number this is. That's just how much area it has, this much area. And if we go backwards, then we look at a number like 1/2. Right? And the area from 1 to 1/2, not 1/2 to 1, but 1 to 1/2 is going to be a negative area, and we can see that at 1/2, whatever value this is, that's how much area there is under this curve. Okay, so that's the connection. Quote, area, negative area. Okay, so that's that's a lot of the explanation here. But I also want to define a number called e, and then we'll be done with this explanation. A number called e. Well, we, as mathematicians, we're interested in certain things, and we're interested in this antiderivative. There must be some value that when we take the antiderivative, we get 1. Okay. So here's a way to look at that. There's some value somewhere where, say, there's a number right here. That's that question mark that I put right there, where the area under the curve is exactly equal to 1. Okay, or that would be equivalent to this, that same x value over here. That this right there is 1. The area under this curve is 1. Right? Because the value of this function and the area under this curve are the same thing. That's what this says. So what is that number? What is that number such that the natural log of that number is 1, or the area under this curve is 1? And it turns out it's this number e. Okay, so it's from 1 to e that we get the natural log of e is 1. The definite integral from 1 to e of 1 over t dt is 1. And it's a very, very interesting number. We'll talk about it more in future sections, but it's super interesting. And we'll talk about properties of logarithms here after I erase this guy here. But one of the nice properties about it is if I said take the natural log of e to the third, okay, well, then using properties of logarithms, I can bring down this power and put it in front of the natural logarithm. The natural log of e we've already said is 1, so the value of this is 3. Okay, so it's got some nice little properties. Here's one of the most amazing, to me, most amazing occurrences of the value e. And I'm just over here looking for a color that'll show up. E to the I, I'm starting out an exponent of e to the I. Remember, I is the imaginary number. This is the square root of -1. So already this seems a little funky. Then I'm going to throw pi in there, right? That's the ratio of a circle's circumference to its diameter, plus 1, which is just the number in arithmetic is 1. It's the basis of our entire ability to do math. So if I take e to the imaginary number times pi, so it's 3.14 of these imaginary numbers, and I raise e to that seemingly incomprehensible number, we get 0. So, one thing that you could notice is that if I add 1 to this thing and I get 0, this must be -1. And this equation, it's called Euler's identity, because this is called Euler's number, and he discovered this identity. It's mind-blowing, because if we raise e, which is just this number that when we take the natural log of e, we get 1, and we raise it to an imaginary number times pi, which just comes from some other area of mathematics with circles and stuff, and then we add 1 to that number, we get 0. It's just like, how can that be? It's just amazing. And I won't really go about proving it. You can look up proofs yourself, but it just goes to show you that e is a very interesting number. It shows up a lot in unexpected places, and in continually compounded interest, and just all sorts of places in nature and stuff. So it's a really neat number. Just introducing it here, defining it, and we will use it more in future sections. Okay, so I'm going to go ahead for those who chose not to worry about this. Okay, so that's just erasing everything. That's alright. That's just a signal to those who have been fast-forwarding that it's okay to come back. So, all that explanation, we could, if we just want to use the information functionally, what that essentially boils down to is that if the definite integral from 1 to x of 1 over t dt is equal to the natural log of x, through just a little bit of work, we could just show that the derivative of the natural log of x is equal to 1 over x. Okay, so if we have a natural log function and we want to take the derivative, it's just 1 over x. Okay, so that's the big takeaway from this section so far, is we can take the derivative of a new function, of a natural log function. And in the future, any log base 10, log base 2, whatever. But for now, the natural log. Now to do this, we should gather some abilities, and that would be properties of logarithms is one. Okay, so we'll go over those properties in general. So as they're outlined in your book, they appear like this. The first one being that the natural log of 1 is 0. We already talked about that. The natural log of 1 is 0. Actually, we talked about that in the explanation, so there it is if you skipped it. The natural log of AB is equal to the natural log of A plus the natural log of B. If you want an explanation of that, again, watch a video about natural logs and their properties, and that'll be explained. This is just really should be a reminder of the properties of natural logs. The natural log of A to the n, we can just bring that n power down. There we go. Another property is that the natural log of A over B, okay, very similar to A times B, would just be the natural log of A minus the natural log of B. So now we have the ability, if we have the natural log of some somewhat complicated function, we can take the derivative of that function. For example, if we had the natural log of x squared, well, keep in mind we can only take the derivative of the natural log of x. Okay, so the natural log of some function. So we can use the properties of logarithms to make this much simpler to take. We could write this as 2 times the natural log of x. Okay, and then if we want to take the derivative of this, well, the derivative of a constant times a function is just the constant times the derivative, and the derivative of the natural log of x is 1 over x. Okay. Another one real quick, the natural log of 2x over x squared minus 1. Well, that would be the natural log of 2x minus the natural log of x squared minus 1. Okay. And the natural log of 2x, we can make this even easier and make it the natural log of 2 plus the natural log of x, and still minus the natural log of x squared minus 1. Notice I did not write the natural log of x squared minus the natural log of 1. That wouldn't be the property. The property that lets me subtract natural logs is if they're divided, if you have a quotient. So here we are going to take the derivative of this function. Well, the derivative of the natural log of 2, what is it? Well, the natural log of 2 is just some number. We could go up to this little graph here. The natural log of, say this is 2. Natural log of 2 is some absolute or some specific whole value. Not whole value, but it's a value. So the natural log of 2 is just some number. The derivative of a number is 0. Okay, so the derivative of this would be 0, because that's just a number. The derivative of 1 over x is 1 over x. Now, we have the need of taking the derivative of something that that we can't simplify. Well, then we just apply the chain rule. The derivative of the natural log of something is 1 over that something. Then we just use the chain rule times the derivative of the something, which is 2x. Okay, so that's the gist. That's the gist of it. And we'll use those properties to, in the next video, take derivatives of increasingly more challenging functions, and then we will see this incredibly awesome, cool trick for taking derivatives using natural logs. It would be called logarithmic differentiation. It's a really cool idea. So we'll work on that. I hope that was helpful. Really get in contact with me and let me know if there's any questions. Thanks for watching.